Hey there, so in this video we are going to go over some trig integrals that require u-substitution but also require some identities, using some identities for changing it up so that we can take the antiderivative. Alright, so we have cotangent, the indefinite integral of cotangent of 7x dx. Now, there's not an antiderivative of cotangent that we can immediately jump to. So we're going to have to think of some identity that we can use and think about what cotangent is. It's not squared, so we're not going to use one of the Pythagorean identities, but it does have, it has a reciprocal identity of 1 over tangent of 7x, but that's not going to do me any good. It is also equal to, if I have cotangent of an angle, it's also equal to cosine of theta over sine of theta. So we have those are our quotient identities. Okay, so if you don't know your identities very well, that's something that we'll have to work on. But let's rewrite this integral as, instead of cotangent, we can write it as cosine of, we've got to keep 7x as our argument in there, over sine of 7x. And now we have to find something to substitute. We're going to find a u that when we take the derivative of u, we get something that's part of the integral. So if you look at this, think to yourself what that might be, and hopefully you're picking u equals 7x. So then du is going to be, well, the derivative of sine is cosine, and then you leave the inside alone, cosine of 7x, but then we have to multiply by the derivative of the inside, which is 7. So, and dx. So we have, if I split this integral, this fraction up, so it's 1 over sine of 7x, and then multiply that by cosine of 7x dx. I almost have this right here, but I'm missing this 7. So I'm going to throw a 7 in right here, but I can't just multiply by 7 without dividing by 7, otherwise I'm changing the value. So I'm going to also put a 1/7 on the outside. And remember that we can only do this, we can only multiply something and then divide by that same thing if it's a constant. We can't do it if it involves a variable. So now, putting in our u substitution values, we have this 1/7, and then it's 1 over, this is my u, so 1 over u, and then all of this is du. Now, how do you integrate 1 over u? I want you to think about it for a second. We just went over this. We haven't done it a lot, but if you try to use the power rule in reverse for this 1 over u, you're going to end up dividing by 0. And so that's when you got to think to yourself, okay, oh yeah, 1 over u, the antiderivative, is ln of the absolute value of u. And because this is an indefinite integral, I'm going to put plus c. Okay, and then now we're going to put in, we have 1/7 of ln of, instead of u, I'm going to write what u was equal to, which is sine of 7x. And we're done. All right, example 2, write this one down. This, to start with, I'm going to separate my fraction again. 1 over cosine squared, of 2x. And then I'm going to put the dx over here. Now, that's the same exact thing. If you multiplied by dx over 1, you would get what we started with. So we want to just pull that dx out so we can really focus on what is the actual integrand, which dx is just telling us we're going to find the antiderivative with respect to x. Okay, so we have some identities we could use. We could use a Pythagorean identity. Cosine squared of 2x would equal 1 minus sine squared of 2x. That's a Pythagorean identity, but then I'm going to have sine squared 2x in the bottom, so that's not going to help me. what we want to use here is the fact that if you have 1 over cosine of an angle, that is equivalent to secant of the angle. So this is a reciprocal identity. Cosine is the reciprocal of secant. So we can rewrite this 1 over cosine squared of 2x as secant squared of 2x. And the reason I want to do this is because I have an antiderivative for secant squared of x, which is tangent of x, but now I have this 2x. So I got to do something with the 2x, and here's where my u substitution is going to come in. If I let u equal 2x, then du would be 2 dx. I have a dx here, but I don't have a 2. So when I rewrite this, I need to, it's going to be the secant squared of 2x, and then I'm going to put a 2 and then a dx, but I also have to multiply by that 1/2 in front. So then we can, if we put our u substitution in here, I have the 1/2 from this 1/2, and the integral of secant squared u, and then I can put this is equal to du. So then you're just going to integrate secant squared of u. I have to keep the 1/2 here, but the antiderivative of secant squared of any variable, any angle, is tangent of that angle. So tangent of u, and then again it's an indefinite integral, so I'm going to go plus c, and put your u back in, which was 2x, and we are done. So to check your work, you can take the derivative of this function that we just got. Take the derivative of the result here. If I do that, then I should get what I started with, secant squared of 2x. I'm going to leave the 1/2 and multiply by the derivative. Leave the constant, multiply by the derivative of tangent of 2x. And I get the derivative of tangent is secant squared of 2x, and then I have to multiply by the derivative of the inside, which is 2. The 1/2 and that 2 will cancel each other out, and again the derivative of c is 0, so I end up with secant of squared of 2x, which is what that checks out, so that's what we wanted to get. Okay, so let's do one more example here. Cotangent squared of 3x. Now, you could try, there's a couple different methods that you could try here. Go ahead and pause the video and try it if you want to, and then come back and I'll show you a method. There's a couple different things you could use here. So what I'm going to use is the fact that I know that I have this Pythagorean identity, 1 plus cotangent squared, it has to be squared, of an angle is equal to cosecant squared of that same angle. Solving this for cotangent squared, if I subtract 1 from both sides, I get cotangent of theta, cotangent squared theta equals cosecant squared theta minus 1. So I'm going to sub this in place of this, except for instead of theta, my theta is 3x. I'm going to have a 3x in there. Now, you may have done what we did in a previous example and wrote the cotangent as cosine over sine. And we could do that. Maybe we'll do this in 2 different methods here. But let's get going on this one here. We've got, I'm going to replace cotangent squared with this cosecant squared 3x. So theta can be anything here, as long as it's the same here, and that's my theta right there. Minus 1, this whole thing. So I'm going to put in parentheses, dx. Now there's a property that says that we can split this up, and we can integrate this, and then minus 1 dx, and I don't need to actually write the 1. So let's integrate. We have the antiderivative of cosecant squared of 3x. Well, we might want to use some u-substitution here, because you might be able to do this part in your head, but if not, we'll just do the u-substitution. Not letting me choose a different width here. So I'm going to let u equal 3x, and then that means du is 3 dx. So I need, instead of just dx here, I'm going to need it to be 3 dx. Uh-oh, my computer's shutting down on me here. I can't just put a 3 in there. I need it to look like this. So I have to put a 3 there, but I need to also remember to put a 1/3 out front. So then we have 1/3 of, and then this is going to become cosecant squared of u, and then this is du, and then minus, and I can integrate 1 dx. If you want to put the 1 there, you can, but it's just going to be x. And I pulled the minus sign out front, so keep that minus sign there. And then the antiderivative of cosecant squared, remember, is tangent. You can ignore this. So I have 1/3 of tangent of u minus x. Put your x back, or your u back in terms of x. Get tangent of 3x, 1/3 tangent of 3x minus x, and that would be your antiderivative. So I said that there's another identity that you might have tried, which would be this one here, where you cotangent squared theta is equal to cosine squared theta over sine squared theta. If you did that and you try, it doesn't actually work. I didn't think about it at first, but if you let u, and sometimes this will happen, you'll choose the u and it doesn't work, then you have to think again, like, what else can I do? And go back to that, the way I did it the first time. If you try to let u equal sine of 3x, then du would be 3 cosine of 3x dx, but I wouldn't have cosine squared 3x. So the u-substitution, I can't square something. I can only multiply or divide by something. That's the only thing that I can alter. I could throw the 3 in, but I cannot make the function squared. So then if you tried to let u equal sine squared 3x, the outside here, when you take the derivative, is 2, so you drop the 2 down in front, and then leave sine of 3x alone, and then multiply by the derivative of sine, which is cosine of 3x, and then the derivative of 3x is 3. You get 6, if you simplify it, 6 sine of 3x, and times cosine of 3x. That is also not equal to what I have up here, so that's not going to work either. So go back to the first version, and we'd have to do it this way to solve this integral. And that happens often when you, especially when you're first starting out, like picking the wrong u, and if it doesn't match the, if your du doesn't match over here, then you got to try something else. All right, that's it.